Okay. So thank you very much for the invitation. I hope you are having a nice workshop next with a bit that I know that I have some beginners here. So today I'm going to talk about the transducer exotic compact objects, but this time in class 1. Okay. So this is a simplified model that started like a development, and ended up in something that was quite innovative. So I think it has many elements that are nice for students. So this workshop is addressed to graduate students, and so I thought it was a nice topic for this. Okay, so the main motivation for the study of the compact objects is because we now have evidence for the existence of such objects. We have the many gravitational waves, the effective gravitational waves of the collision of the compact objects, and we have also seen radio waves, emission of the radio waves, using interferometers. Observation is around very compact objects. So everybody looks like compatible with the risk of relativity. So we generally speak about the fact that we have observed black holes, but we don't really know if these are the black holes predicted by general relativity or if these are different compact objects. Okay? Because we don't have yet enough precision in the measurements to really determine the existence of different fractions and other properties that would identify black holes as the object responsible for we observe. Okay? So, also there are reasons to believe that the relativity is not a final theory, because it has difficulties to make it compatible with quantum theory. The theory, the relativity is a geometric theory of gravity, and this geometry can develop singularities, which are something that should not exist on physical grounds. Okay? So we do believe that the theory must be modified at some point, or that something should happen that cures those singularities, and then probably the active black holes to exist. I mean, black holes are understood as objects with an event horizon. If they exist, they should be at least slightly different from the risk of the data. Okay, but the thermal structure should be modified. Also, another possibility to get rid of the problem of singularities would be to change the conditions for the matter fields that lead to the development of the singularities. Okay, as you know, the singularity theorems of Penrose and Hawking and many other people, they are conditioned by some properties of the matter fields. So if the matter fields have different properties, then singularities could be avoided, at least in some cases. So it is important to explore the existence of exotic compact objects in at least two different directions. One would be extensions of the Earth, another would be extensions of the matter. Okay? So in this talk, I'm going to explore in the second case. Okay, usually, probably 95% of my talks explore extension of the relativity, but today, you are lucky, I'm not speaking about that. So I'm going to speak about something divertimento, about what can happen in general relativity if we consider exotic matter. Okay? Okay, so since this is an exploratory paper, exploratory work, so the time efficiency, as I say here, it is always best to consider simple problems. Okay, this is why I was looking at this problem in a simplified scenario, which is a simple scalar field in total one. Okay, and we consider as many simplifications as possible, not too many. Okay, just to try to obtain analytical results. Okay, so in that sense, I think that this paper is interesting for the physical results, the physics that is behind, and also because of the mathematical methods that are needed. Because basically, all the mathematics that used here is what I teach in my course, my undergrad course, in the second degree of physics. Yes, in the second year of the physics degree. Okay, so additional motivations that are necessary here. Usually, when we explore, when we look for exotic objects, in compact objects, in theory beyond the relativity, using a different approach, this modified gravity. In many cases, we find, or we have found, wormholes. Okay, so we would say that my favorite alternative object is a wormhole. Okay, and because basically I have learned with them, so I have found them in many different works without sketching or without looking for them. So they simply arise, and here we have several papers. This first one was focused on the so-called Eddington-inspired governmental theoretically theoretical formalism, coupled to a free-scale action. And in this scenario, we found that wormholes arise naturally. Okay? In this other work, we also found wormholes that we consider other theories of gravity, or theoretical formalism. And here in quadratic gravity, this is the relativity plus R squared plus x squared correction in collaboration with Professor Cristino and Nam. We found that wormholes also arise in this theory of gravity. Actually, the geometry of this wormhole is very similar to what found here. It's something we explored in our work. And more recently, doing numerical analysis, exploring Boston stars, which is a theory physics, real physics, using numerical relativity to build models of Boston stars in quadratic of gravity. We managed to build the static solutions and use them as initial data for the time evolution. So we prepared this initial configuration to produce the gravitational collapse, and then we found that inside those that these objects collapse, these stars collapse, they form black holes because we have to be present. But then inside there is something like a wormhole arises. Okay? So this is a piece of evidence suggesting that these kind of objects with wormhole topology, at least, because these ones are hidden by an event horizon, these kind of objects could be formed dynamically. So this is very interesting. So at least we have a confirmation that by using initial reasonable data, time evolution can generate this kind of topological structures, which is a good result, a positive result after so many years of speculation and finding static solutions. So having them from dynamical processes is always very satisfactory. And more recently, we have used this result to explore other kind of structures. This is this other paper by Renan and Andreu, Flavio, Professor Crispino, and myself. We use a construction inspired by the dynamical formation of wormholes, just to explore what would happen if these structures didn't have an event horizon. Okay, so these are different works in which I have been exploring exotic objects, and we always find wormholes. But today I'm going to follow a different path. So we are going to consider a new simplified model, a 2+1 dimensional scalar field model in general relativity. So as I said, not every day I speak about general relativity. So this is a very unusual talk. Okay, so let me explain the model. I will try to be brief today because I don't have too much to say, but this is the basic idea. So this is the action of general relativity in 2+1 dimension. This is why we have this 3 here. So the gravity action is standard GR, but the matter action is a non-canonical function of the kinetic term. Okay, this Y, this capital Y, is represents the kinetic term, okay, of the scalar field, And this function L is some function, a priori is not specified, that determines the specific form of the matter Lagrangian. Okay, if L is simply Y, then we would have the canonical scalar field. Okay, but if L is something different, so we would have something different. So from this action, we can compute the stress energy tensor, which takes this form. So I explained the notation. This Ly is the derivative of L with respect to the argument of Y. And then the scalar field equation, assuming staticity and circular symmetry, is circular and not spherical because we are in 2+1 dimensions, okay? So the scalar field equation takes this form, okay? And then what we want to do is to trivialize this scalar field equation, okay? There are many other ways of exploring the dynamics of scalar fields, but we choose this one, okay? And this one is that we transform this generic equation, okay? We use this line element, okay? Note, pay attention to the structure, which is not standard, okay? The GTT component is standard, but the GXX component is not. There is no radial function, it's not obvious radial function. So basically, our radius is the inverse of this W function, okay? But the most important thing is this sector here, the radial part. Because with this choice, note that this parametrization uses the derivative of the scalar field Lagrangian in the line element, okay? With this parametrization, the scalar field equation is simply this one, okay? So this is what I mean when I say we want to trivialize the scalar field equation. What this means is that the scalar field is simply a linear function of the coordinate x, or in other words, we are using the scalar field as the coordinate for our line element. Okay, so we are going to express everything in terms of this scalar field, and then at the end we will transform this function omega into the usual radius, and we will interpret the results in terms of the usual intuitive radial coordinate. Okay, but for mathematical simplicity, we use this parametrization. Okay, this is just mathematics. Okay, very good. And then from the Einstein equations, we get these these various representations for the components of the Ricci tensor. And these are the key objects that we will use. Okay, as you can see, we have written Einstein's equations as Ricci equal to functions of the matter field. Okay, so we have here the right-hand side is the matter, the scalar field Lagrangian, the derivative, the kinetic term. Okay, and then we have three equations, and we have to manipulate them to find the solutions. Okay, it's that simple. Okay, so the first thing we do is we take this equation here. Okay, the first one, the RTT component, the first component of the Ricci tensor, and then we observe that written in this form, okay, what we have is a first-order linear differential equation for the variable AX. So AX is the first derivative of the metric function A. Okay. So this is a first-order linear differential equation. As I teach in my course of differential equations, you can find a formal solution in this form. Okay, so this is very beautiful. Note that, but it's completely useless. Okay, it's beautiful because it is compact. It allows you to find this first integral, but you cannot perform this because you don't know the form of L and you don't know the dependence of Y with X. Okay, so we cannot do anything. But if you look at the structure of this quantity here in the integral, you see that by taking a power law of the kinetic term, then this quantity becomes simply a constant. Okay, and so if it is a constant, we can integrate. So that's what we did. Okay, no wonderful reasonings, just mathematical simplicity. Okay, we are doing just something very simple. Okay, so with this choice of Lagrangian, we can integrate this quantity, this constant, which is basically alpha times lambda times alpha. Lambda is a parameter that contains the dimensions of the kinetic term of the Lagrangian, okay, just to make it dimensionally correct. So it could have two signs. Also, the signs are important, positive or negative. And then, this alpha that appears everywhere is just the power of the
that is raised the kinetic term. Okay, so basically we can integrate this, and this delta 1 can be written in this form. Okay, so as you can see, it is linear in x because of the integration, and this x1 is just an integration constant. Okay, now so we have made some progress, and then we can progress further by combining these three equations in this form. Okay, this combination leads to this this combination of first derivatives, but since we now have an expression for ax, so we can take this ax, put it here, and then this allows us to solve for omega x. Okay, we can find analytically the function omega. So our choice for Lagrangian was based on this equation. Just for simplicity, we wanted to find an exact integral, so that justified the choice of Lagrangian, and this allows us to obtain an explicit expression for the function omega, okay, for this w. And at this point, we can see that there are some dimensional constants. This R0 has been introduced just for dimensional purposes, just to illustrate that omega, that this w is the inverse of a radius, so it has dimensions of length. This x0 is just to remove dimensions, and this x1 was coming from the free constant of integration from this integral. Okay, but if you remember the form of the gravity of the action, okay, that only depends on the kinetic term of the scalar field, and the scalar field is our coordinate. So in the action, we only have derivatives of the scalar field. So this means that there is a shift symmetry, and therefore a shift in the coordinate x is equivalent to a shift in the scalar field. So this x1 constant is irrelevant. Okay, so we can just set it to 0, and that's okay. So we can forget about that thing. Okay, very good. So now we have solved for the function w. A is almost solved. We have the first order derivative, and then we can come. I think that we have to come here to this equation here, the angular part, and here we insert this result. Okay, so inserting this result here, we get a first order differential equation for the object yx, the kinetic term. Okay, there are other ways to solve the equations, but this is very, very nice because, as I told you, this allows me to make contact with my course on differential equations, because this is simply a Bernoulli equation. Okay, look, this part is linear. This is a function of x that we know. This is another function of x that we know, and this is a power of y. So the nonlinearity of the equation is of this type. So there is a transformation of coordinate, of a redefinition of variables that allows to write this equation as a linear first order differential equation, and then we can find an exact solution. So we do this, we find the exact expression for y and in terms of x, and using that we can then solve for a. Okay, so it's mathematically it's very simple, and then we find that the exponential of a, the GTT component, can be written in this way as the sum power of this function delta 2, and this delta 2 has some integration constants, but after some simple reasoning, we find, under definitions, we find that the relevant structure of the solution can be written in this form. Okay, that there is some power of r here, and then this quantity must be dimensionless. So we redefine all these constants in terms of another radial big R0. Okay, and the sign of lambda is what we put here as plus minus. Okay, so we have absorbed all these constants in this R0. So basically, as you can see here, the exponential of a will be some power of this quantity. Okay, and the power is minus gamma, and gamma is also here inside the bracket. And this gamma is defined in terms of alpha. Remember that alpha is the power of the scalar field Lagrangian. Okay, and the line element now, using the usual radial coordinate, takes this form. Okay, which is very nice because we have an exact analytical solution for this configuration. So we have general relativity with a scalar field, and we get this analytical expression. Here we have made some choices, okay, because what we were looking for are asymptotically flat solutions, because we want to make contact with gravitation, at least in a simplified model in 2+1 dimensions. This would be like, in some sense, like looking at the equatorial plane of some compact object, okay? And then, so in order to get asymptotically flat solutions, we need to restrict the values of the parameter gamma. So gamma must be positive, okay, because otherwise we wouldn't get asymptotically flat solutions. Note that this delta 2, when r goes to infinity, should go to 1. Okay, for that, we need that gamma is positive. Okay, and to have a positive gamma, we must restrict the powers of the scalar field Lagrangian to this interval. So the Lagrangian wire to the power alpha is between 1/2 and 1. Okay, still it's a small range of parameters, but you know we have to pay a price. It's a exactly solvable model, very simple to reason and motivate, and it even leads to asymptotically flat solutions, which is highly non-trivial. Okay, even in general relativity with the scalar fields. So this is the two kinds of solutions that we find. Okay, and the two kinds depend on the sign. Okay, we have a plus and a negative sign. The plus sign is when the lambda parameter is positive. The minus is when lambda is negative. Okay, so if we go back to the definition of the scalar field Lagrangian, when lambda is positive, we have a standard matter field. But when lambda is negative, we have something with negative kinetic energy. So, and they don't have good reputation. These things with negative kinetic energy are typically, typically with good reasons, they are criticized because they can lead to instabilities, because you can extract an arbitrary amount of energy from the vacuum. There is no ground state because you can go down to minus infinity energy. So, so this is what is called a ghost. So this generates a ghost instability in some cases. So there are ways to remove the instability. But anyway, so let's say that the negative sign has bad reputation. Okay, why? Because the normal is that matter fields be attractive. So, and from this line element, we can see that the GTT component has this structure. But if you consider the expansion of this quantity very far away, when R is much bigger than R0, then we can expand this quantity like 1 minus this function, okay? So, and if you remember in the Schwarzschild solution, the GTT component is 1 minus 2m over R. So when you have 1 minus something positive, you are dealing with positive attractive gravity, okay? So this solution represents attractive gravity, okay? So this is why the positive sign is describing regular matter with attractive gravitational properties, okay? And this guy is the one that has bad reputation, okay? Because when you expand this far away, you see that it is not 1 minus something, but it's 1 plus something positive. So this represents like a negative mass in the Schwarzschild case. Okay, so this is generating repulsive gravity. Okay, so we have these two kinds of objects. Okay, so we have to explore their properties. And well, what can I say? Well, this guy here, the attractive one, is an asymptotically flat solution with no horizons. Okay, because this function doesn't vanish anywhere. But when r goes to 0, this denominator goes to infinity, so this function is 0, okay? And also this one goes to infinity, this is 0, so the geometry is not well behaved. So when r is 0, goes to 0, we have some problems. So this will be, without doubt, a naked singularity. It's attractive gravity, which is good, but then it's a naked singularity, which is bad. Okay, but then let's have a look at the other one, the bad guy. The bad guy, the repulsive gravity guy, has some peculiarities because when r is equal to 0, when r is equal to capital R0, then this function vanishes. okay? And then the GTT component becomes infinite. And this is unusual, okay? So if we look at this, everything suggests that this would be, that this point or this region will be an horizon, but it is not a killing horizon, okay? So we need to look with more detail to the physics of this line element. What is this object representing? Okay, this is really what we are interested in, okay? So since I know that many people love scalar invariants, curvature invariants, just I will show you that what the Ricci scalar and the Kretschmann scalar look like for these two solutions, okay? In the positive case, the Ricci scalar and the Kretschmann are always positive, okay? And when R goes to 0, this is infinite. So as we suspected, this represents a naked singularity. Now, what happens with the negative sign? Well, the negative sign, we saw that the metric is only well-defined down to capital R0. And when R is equal to capital R0, then this quantity vanishes. And this other quantity also vanishes. So all curvatures, or at least these scalar invariants, vanish at the region where there could be problems, okay? So we need to look in more detail to what's going on in that region, okay? Because curvatures are finite. So we have discarded the attractive case because it is discarded in terms of it doesn't bring any interesting new physical insight because it represents a naked singularity. But this one, the negative one, we still don't know what it is. So we need to understand this guy. And then another source of information are geodesics. We can explore the geodesics of these two geometries, these two line elements. And then we find that in the attractive case, the geodesics are incomplete as we approach R equal to 0. So as we approach the divergence of the curvature invariant, the center, basically, the geodesics are incomplete. So this confirms effectively that the space-time is singular, okay? But when we look at the geodesics of the repulsive case, we find that they are complete, which is quite curious, okay? So we have an object with repulsive gravity, with finite, actually vanishing curvature invariance on a circumference of radius capital R0, okay? And it turns out that the geodesics take an infinite time to reach this central circumference. So this is a representation of the behavior of the geodesics for different values of gamma, okay? This is our line element. So the dashed line simply represents geodesics in Minkowski, okay? In Minkowski, we have ingoing geodesics in blue, outgoing geodesics in red. So we see that far away, our model recovers the geodesics of Minkowski, but as we approach this central circumference, the affine parameter diverges, okay, for outgoing and for ingoing. So this means this is what justifies that this internal circumference, where this quantity vanishes, is actually a boundary of the manifold, okay? This we cannot get inside the circumference. We cannot reach values of R smaller than R0 because any geodesic will take an infinite time to approach R0. So it is not physically possible to go inside. So the region of the domain where R is smaller than R0 simply doesn't belong to our spacetime. Okay, so this is quite an unusual object. So this is not, this circumference is not a wormhole throat. And geodesics take an infinite time to get there, and the internal region is simply absent. So there is nothing. That is not a part of spacetime. So our spacetime basically is like a plane from which you remove a central circle. You remove this circle, the boundary is a circumference of radius capital R0, and then this is the manifold that we have in this configuration. Okay, So if we, just by curiosity, we represent the kinetic energy of the scalar field for this configuration. So this is the function in particular. You can see a cross section of the kinetic energy profile like this. Okay, it goes to 0 at infinity. It goes to 0 again at the boundary, at the internal boundary on this circumference, and it has a maximum. And this maximum can be determined analytically. Everything is analytical here. And when we represent them, it looks like this. It's in 3 dimensions. It looks like a volcano. So it's a volcano. It has this property. So this is a curious exotic compact object in 2 dimensions that represents an asymptotically flat non-singular spacetime. Okay, and there was nothing physical behind the construction of this model, only mathematical simplicity. So maybe we could find objects of this kind better motivated physically. Okay, but at least this is what we have. And then just let me think about what this may mean. Okay, first of all, say that we have a non-singular space-time with an internal boundary that has been found for in a 2+1 dimensional scalar field model based on mathematical simplicity arguments. Okay, this geometry is geodesically complete. All curvature invariants are smooth, are well behaved. Okay, the completeness of the geodesics, note that has been achieved non-perturbatively. And what I mean by non-perturbatively is something like this. As gamma goes to 0, you can see that this is basically Minkowski spacetime everywhere except at the location of the boundary. Okay, that there is no enough numerical resolution here, but you can see the trend. Okay, from the other cases, as gamma decreases, the divergence in the affine parameter appears closer and closer to the internal boundary. Okay, this is what I mean by non-perturbative completeness of the geodesics. So what this means is, well, this may mean nothing, but at least it illustrates some aspects that are interesting. And it's the fact that with exotic matter sources, we can avoid geometric singularities, space-time singularities. We can restore geodesic completeness non-perturbatively, okay, in general relativity, because we are in general relativity in 2+1 dimensions, but it's GR. You are GR with exotic matter. So this kind of exotic matter with negative kinetic energy could help avoid singularities in this interesting way. And this interesting way is particularly interesting because it does not represent a typical compact object, right? Like a wormhole or a kind of exotic star. This is something in which the interior does not exist. There is not a center. Okay, in this case, there is a circle that does not belong to the manifold. Okay, so it would be nice to see if these objects could be extended to 3+1 dimensions, and we could find like a scalar field distributions of this kind. Okay, because typically when we construct models like boson stars, we set boundary conditions at the center of the star and then far away, where we believe that there should be the surface or some criterion for low density. And then we integrate and backwards and forward just to find the right solution, okay? But here there is no center. So it is not clear how the usual approaches to set boundary conditions, to explore this kind of scalar field configurations could be implemented in 4 dimensions, okay? So because if we had an object like this in 4 dimensions, basically it would represent like a boson star, simply that without the center. You just remove a sphere, a small sphere from the center, and then there would be a boundary, a spherical surface representing an internal boundary. Okay, so it would be nice to see if what we have called here lambda, which was a constant, maybe we could model it in terms of another scalar field, so that we could tune the sign of this parameter and see if we could build stellar objects in the sense that they have attractive gravity outside. So all the phenomenology that we know about astrophysics could be reproduced, but if in the internal region, in the innermost region where a singularity could be formed, we remove that region and switch this new interaction, this new exotic form of matter that, who knows, it could exist at the end stages of the collapse of some usual boson stars. So we need to interpret this as the possibility of the existence of a new form of matter not yet observed, like dark matter, maybe some kind of dark matter that in the last stages of gravitational collapse, they could develop these exotic properties, generating a negative or a repulsive form of gravity, and avoid the singularity. So we would like to explore these kind of configurations in 3+1 dimensions, just to see if they exist, if they can exist, how weird they are, if they are something reasonable, if we can put regular matter on top of them or not, and mainly just to see what would be the observable features of such objects, because they are not like typical boson stars, they are not like black holes, they are not like wormholes. They should have different properties, okay? So, and that's why I found this model, this simple model, this toy model, interesting, and I wanted to tell you about these results. Okay, so this paper has been accepted for publication in Universe, and it will be one of the covers of it will be the cover of the next issue next week. So that's all I wanted to tell you. Thank you so much.
So okay. Let's thank the speaker. Okay. So Hannah is going to make a question through my microphone. You can speak.
Yes.
That's okay.
Hi, Professor. Can you hear me?
Yes, very well.
Okay. Let me. Okay. So have you tried to model this kind of thing with a fluid laboratory, for example? Because I think you can put something like a cylinder at the center, not at the center, but at that particular circumference that could be used as you see the boundary of your model.
Yes. Can you repeat, please? I want to understand your question correctly. Is it, yeah.
Okay. So, did you consider some fluid laboratory to model this kind of solution? I mean, maybe with analog model, you can consider a cylinder at the center, and it could be used as a boundary. That boundary you talk about.
That's a very good question, Renan. Yes, I like the idea, because I would add that with a cylinder in laboratory analog, I would use probably a medium with a refraction index that diverges as we approach the cylinder. In that way, geodesics would take an infinite time to get to the cylinder. So maybe that could work. That's very interesting. Yeah. Thank you.
Thank you.
Gonzalo, I believe that there are questions, but we really are facing some sound problems here, and I think it will be enough. Okay. We had one question, so it's a progress already. We did not have anyone before.
Okay.
from the audience because of our sound problem. So I would like to thank the speaker once again. So I ask you for a round of applause. Thank you very much, Gonzalo. It was excellent. Thank you.